long before they discovered helium on Earth, and that's because helium doesn't react with things. It's incredibly light. Once it's in the atmosphere, it actually escapes into space because it's going so fast, right? So there's your trivia. Now, let's do the math that we need to do with this. All right. Okay. Now here is the pattern. If you want to pass those to the front, I will start the box here, and you can just carefully put them in there. You need to put that envelope off to the side. Okay. Here is this pattern that they follow, and this pattern looks like a kind of an interesting pattern, doesn't it? That's an interesting pattern. You have to look at that and say that even follows some sort of mathematical formula, doesn't it? Okay. In fact, a high school teacher in Germany came up with a formula for it. This, by the way, really ticked off the physicists of the time even more. Okay? Because here's this formula, and clearly the formula has got this sort of hidden, sort of deep mathematical meaning, yet we still have no clue. Even cooler than this was that Rydberg's formula predicted not only the Balmer lines, which were the visible ones, the ones we could see, but predicted the existence of, in other words, if you make this first number a 2, you get the Balmer series. But what if you make it a 1? What's that? Well, we don't even know. That has so much energy, by the way, that it's ultraviolet. And if you make it a 3, then it doesn't have enough energy to even be seen. It's infrared. Just set them on the counter. Okay? So that is sort of an interesting thing in and of itself, is that it not only did this thing predict the lines that they could see, it predicted the existence of these other series that were later discovered, right? Now, does anybody want to make a guess? What do you suppose these little numbers are? The orbital levels, there we go. N equals 1 is the ground state, 2 is the, oh my gosh, right? Now this is, of course, that's the Bohr model, so Bohr had to figure this out. What Bohr did was he went from this is the answer in the back of the book, but he didn't get it just ad hoc. This basically is just some ad hoc formula that makes it all work to fit the experimental evidence. What Bohr did was he set up an orbit situation, and they do it in the book. They actually derive it in the book. He got a Nobel Prize for it, so if you want to, it's just algebra, and it takes like 20 minutes to explain on the board. I'm choosing not to do that because we don't have time. Okay, but you can actually go through and do the algebra that leads to something somebody got a Nobel Prize for. Okay, so what Bohr does is he actually takes things like the charge of the electron, the charge of the nucleus, and he sets up a situation where the electrostatic force equals the centripetal force. And then what he chooses to do is he quantizes something called angular momentum. And those guys that were doing the flips, right, Jason and Matt, right, okay, they talked about angular momentum. He quantizes angular momentum. Why did he do that? Did he know the answer? Yeah, and something had to be quantized. This is quantum theory, Planck quantized energy, right? So Bohr quantizes something called angular momentum, right? And he comes up with the Bohr model, and these are the orbitals, right? There are only certain stationary states that are allowed, right? Why don't they radiate energy? Like Rutherford's atom had to radiate energy. Why don't they radiate energy? I don't know. Because they're stationary, right? That's kind of weird. Is there any situation in physics where we've had something that's moving yet seems stationary? Is there any sort of situation like this? I mean, I don't want to let the cat out of the bag. Right? Have we ever had a situation where something moving appeared stationary? Holy cow. Are there only certain allowable standing waves that can be on this thing and no other ones are allowed? Is that possible? Yeah, this is not how Bohr approached it, by the way. Bohr did not approach it this way. He just ad hoc, he just sort of said, let's quantize angular momentum. Because, by the way, that's how you get the answer in the back of the book, right? Okay? But I'm foreshadowing. Okay? Now, these are the Bohr orbitals. This is n equals 1. That's the ground state. This is 2. This is 3. All of those lines, all of those spectral lines that you saw were the light released by electrons making a quantum jump from an upper level to a lower level. This is bizarre stuff, okay? We're talking about the electron disappearing from here and appearing there, yeah, and not being in between. We're not talking about like, I'm here and now I'm here. Because in between, I was in between, right? This is quantum stuff. This is really bizarre stuff, right? So when it makes a jump from this thing to this thing, a quantum leap, as it were, okay, which you could think of as a transition between modes. Like you're playing your trumpet, you blow at one level and you play the low note, right? You blow a little harder and you get the next note up, right? You don't play any note in between, do you? Well, I mean, you know, I do, but right? But anyway, that's the notion, is that you go from here to here. It's a quantum shift. There's no allowable state in between, so it just doesn't exist. So when you go from here to here, that's the first Balmer line, second Balmer line, third, et cetera, right? This one is visible light. These energy differences correspond to energy differences that we can see. These, look at those. Is that more energy or less? More. Yeah, kind of way more. That's ultraviolet. Ultraviolet is more energetic photons, right? This one is much less energy than visible, so that's infrared, right? It's off the low energy end of the spectrum, right? So there those things are. Yeah, you could just keep going, right? The next one is called the Raffo series, right? No, I don't know. The next one's the Murray series. One after that could be the Raffo series. Because I saw that question coming slightly before you asked it, and threw the Murray thing in there first. Like, I call it, you know, dibs. You didn't hear me dibs it. It wasn't a vocal dibs. You know.
Nonverbal dibs. Jordan.
Nonverbal dibs. So I think you have, don't you have this example on your little sheet, right? What is the wavelength of the first Lyman line? Lyman, it's like, isn't that like Sprite? Okay, now, G, these are not very hard. All there is there's a graph reading piece where you find the energy difference. That energy difference becomes the photon energy. And then isn't it just hc over lambda? So there's a graph reading part, where we find the energy difference, right? And then isn't it just hc over lambda? And then like turn it into, right? So just remember, there's a graph reading part, right? And then after that, it's just all hc over. I don't know why this is hc over lambda, but it just is, right? Okay. So the first Lyman line is this guy right here. When they say first, they mean least energetic. So when you're doing these problems in the book, there it is. When they refer to the Lyman lines, find this diagram in your reading and use that. So in the problems, that's what they're talking about. The first Lyman line goes from negative 3.4 to negative 13.6. Why are they all negative? Here's what they're saying, right? They're saying these energies here are the energies needed to take the electron off the atom and move it infinitely far away. It's like the work function, yes? Okay, only the work function is like for the exterior electrons, the outer ones, right? So it's like, you know, here-ish, right? Okay, so, but it's not the same thing. There's some difference, and I'm not exactly sure what that is because I'm not very smart. Okay, but anyway, so anyway, this is the energy needed, and so the ground state is very tightly bound. You need to put in 13.6 electron volts of energy to get that electron off of there, right? Okay, so what is this energy difference? Yeah, this thing, the electron loses 10.2 electron volts of energy, correct? Where did that energy go? Did it turn into a photon? Oh, indeed it did. So isn't this problem just simply what is the wavelength of a 10.2 electron volt photon? And we're good at this. At least I hope we're good at this. God help us if we're not good at this, right? So the first thing I'm going to do is I'm going to turn this into joules. That would be kind of a joule of a suggestion. Trying for a laugh, realizing that you are somewhat bored. Okay, so 10.2 times 1.602 e minus 19. And this is 1.634 times 10 to the minus 18 joules of energy, right? And now the wavelength is going to be, well, E is, bless you, hc over lambda. So lambda is hc over E. So that's going to be 6.626. I'm getting emotional now. And that's joule seconds. C is 3E8 meters per